Real pleasure to have him back here on
Thank you.
campus. And we're going to learn a little bit more today about sources and mechanisms of sediment production in Minnesota rivers, which is a favorite topic of Satish's.
Yeah,
So
right.
thank you, Satish.
Yeah, thank you, Tim. Hi, Brent. Come on in before I start. Well, it's good to be back. I think sometimes you just stay at home after you retire, you just get mischievous, and this is a result of what I've been working on, and I thought it'll be good to just come over here and talk about it. Please don't compare my presentation with Laura's presentation 2 weeks ago. It's a long, winding presentation, but I'll give you an overview of much of the work that we have done in this area, and I'm still working on it. And there are two objectives for giving this presentation. I often come over here on the Zoom, see students' presentation, and they have a little reel in the agriculture field, and they talk about soil erosion. And I thought they should be a little more familiar with the sources of sediment in the river rather than just that little reel. So this is to expose the students, staff, and faculty to various sources and mechanisms of sediment in our rivers. And this is the second in the series of seminar. About a month ago, I gave one to the agencies on the role of precep and tile drainage on river flows. So this is the second. Try to convince them that holding water on the upland is a bad idea and lead to more sediments and more nitrogen in our rivers. But before I go in there, first, happy Valentine's Day to all of you. But I want to dedicate this seminar to one of my friend and colleague, Dr. John Moncrief. He passed away last year. He was an extension soil specialist and professor of applied soil physics. We jointly co-advised many students over the 15, 20 years. He was very good in the field work, and I learned a lot from him. And it's kind of bad that he's gone so soon. This is a group of our students at one time, postdocs and technicians and foreign visitors from Germany. I don't want to go into each name over here and what they're doing because my presentation is already too long. So the outline of my presentation is I'll give you the context, and then I'll talk about the Minnesota River Valley and the Red River Valley. In the Minnesota River Valley, I'll discuss the bank erosion, extent of it and the mechanism, as well as the extent of field erosion and the mechanism. And then in the Red River Valley, I'll just talk about the bank erosion, and then I'll end up with a one slide on implication, or a few more slides than one slide on implications. The whole reason for doing this is that Minnesota has a statute. The agencies got $2 million a couple of years ago, and then they got 17 million last year. And I understand they're trying to get more money, and their idea is to hold water on the land to improve the water quality of the Minnesota River or other rivers. And my concern is mostly on the red line text over here, retention structures and basin, soil and substrate infiltration, they want to increase it, wetland restoration, creation, and enhancement on the upland. That's where my concern is, and so this talk is more in that context. They have funded many studies, and the reason for doing their holding water on the land is this is their premise of those studies. And they say increased flow in the river is due to tile drainage. More flow means more undercutting of the river bank and thus bank sloughing. And reducing flow means less sediment transport, which is correct. But I'm not sure they're doing it in the right context. However, they are ignored the climate characteristics because we have a lot of large storms that are coming in the present climate, and that has some impact. And they're also focused on only single issue, which is sediment control. And they're not looking at by storing water, how it's going to affect the crop productivity and the nitrogen losses. So the first is they are assuming there's an undercutting of the river banks, and that's why the banks are coming down. And you don't need a river to have a bank sloughing. This is in Cortland, Minnesota, near New Ulms on Highway 68. And there were 4 or 5 inches of rainfall, and it lost about 2,000 cubic yards of material. John Alexander and I went over there in August of that year. And this is after cleaning, this is how the bank looked like. There was still some failure going on. There were a lot of seepage spots on this bank. This is another example that we don't need a river to have a soil material go into the river or the creek. This is in Carver Creek, happened July 2012. And the farmer had planted beautiful straight rows of soybeans, and there was a lot of material taken out. From here, they had about 6 inches of rainfall over a week period, and they lost about 5,000 cubic yard of the material. This is Doug Miller, who worked for NRCS, and he showed me where this place was. And Drew did some experiments over there too. And this is Ashley Grutner, and that's me. You can see that Carver Creek is there, which is at least 10, 15 feet deep below the edge of this field. And also it's all extended area over there. So if there was any flooding, water would be spreading there and not coming over here. This is not a very big watershed, but you can see this wetness over here. And that's where the glacial till is. The water hangs over there. And it just, because of all that rain, it just kind of slumped and taken out. Now, the second part of their premise is that tile drainage increases river flow. And I've given this seminar many times, and I think they just don't understand the physics of tile drainage or what tile drainage does. So here is a tile sitting, this is a cross-sectional area, cross-section of the soil profile. Here's a tile over here. If the water molecule comes here, has to travel some distance. This is not a swimming pool. There are soil over here, soil particles. And the water has to go in between the soil particles to reach here. So it might take about 3 days or 4 days or something getting over here. But the water molecules in between the tile, if it comes over here, it has to travel this stream tube to get to the tile. And that could take 30, 40 days. So if there is an impeding layer over here, and there is no tile line, then it's going to take a long time, maybe 90 days, 100 days to get to the river. But in this case, when there's a tile line, it could be anywhere between 3 to 4 days here and 30 to 40 days over here. And we've done some calculations on that thing. So what it's doing is it's changing the travel time. It's just taking the water out within 30 days or 20 days. It's not taking the water physically, making any change in the water balance, because what controls the water balance is the soil particles and the plants and what the rainfall is. So in summarizing, the other thing that you want to remember is that let's say this space is empty over here because the water table has gone down, and then you got a rainfall. The water that gets out of that tile is not the new, not most of that is not the new rainfall. It's the old water that's still traveling over here because this water is pushing it down. So people don't understand that this, by controlling, storing the water over here, they don't know how much water is in the soil, and they're going to be causing more damage. So the role of drain tile is they change the travel time for water to get out. And the farmers are doing it because they need the zone of aeration to grow plants. Initially, it's the old water that's coming out. This might be a little new water over here after 3 days, but most of this is the old water that's sitting. And more drainage means there's going to be more space available for the next storm, and that's very important in our climate. So as I said, the quantity of water that gets out of the landscape is controlled by water balance. So here is a precept. Some of that converts into evapotranspiration. Some is stored in the soil, and balance of that is what goes into the river. So here is plotted is the stream flow versus the precept for 2 different periods. And this is a blue line is the initial period, and the red line is the second period, the recent periods over there. So the only way this flow is going to go up if our precip goes up, or ET is less, or there is a more water from the previous year that's stored in the soil, and this water is contributing to P, so we have total more water in the soil profile. So when you look at this line has shifted in recent years, and the reason it has shifted it because we are getting too much water and our soil storage term is increasing. And most of the water is coming, most of the precepts which are excess, they're coming in the fall. Our soil profiles are empty at that time because the plants from the previous summertime had taken over the water. So in here, if you look at these pink points over here, there are 6 pink points, they correspond to the red line. So there are more years when there was a water brought from the last year and contributed to this flow. In the previous, the blue line and the aqua triangles, they go together. So it's not the tile line that's causing this increased flow. Is because we're getting more precip, and also that some of the precip is stored in the soil and carried to the next year. People for 10 years, agency folks wouldn't believe me the climate is changing. Okay, no, everybody agrees on it. Here is a precip versus time, and this is the initial period that I had in the previous slide, and this is the second period. So you can see that this black line is the evapotranspiration of 600 millimeter. And there were many years, there was not enough precip in any given year to meet the ET. And in here, the less number of years. The other is you'll see there are a lot more years which are very high precip values. An example of 2010, very high precip value, and 2011 and 2010 had about the same stream flow. Okay, because some of this water was stored in the soil, brought into the next year, and contributed to the flow. So in summary, increased precipitation is the reason for increase in river flows. There's a more precipitation is occurring in the fall, which is stored in the soil, carried over. And the third reason is there is also a little bit less evapotranspiration because evapotranspiration demand is less because we're having more frequent rainfall and the vapor pressure deficit or the relative humidity is different. I looked at the data from St. Paul campus on pan evaporation, and it's been going down over the recent years. So all of these three factors that we have, they're contributing to more carryover of the soil water from the previous year into the next year and contributing to flow. So this was a kind of rebutting some of the assumptions that studies that agency folks have been just kind of going with it. Now I'm going to go on to the sediment sources and the mechanism. So my presentation is mainly concentrated on the Minnesota River Valley and the Red River Valley. And in the Minnesota River Valley, I'm looking at the greater Blue Earth River basin. And within that, I'm looking at the Blue Earth River, Blue Earth County over here. This county has the most river miles of any county in the state of Minnesota, okay? And most of these rivers are flowing to the north. Here's Mankato. So when Mankato is still frozen, and this is kind of thawed out, then there's going to be some ice moving around and gouging of the river banks. So if you go in that basin, you'll see along the river, you'll have a bank something like this, and you have an agricultural land which is very much like this, which is relatively flat. But there are a lot of depressional areas, there are slight depressional areas, and they're interconnected. There's not enough storage space in there. And in the winter time, if this is facing south, there's going to be probably at January 10th, there might be a 32, 33 degrees, and the top 1 centimeter or 2 centimeters of the soil will just slump and come down over here. And this is right next to the river. So if you look at these two, this sediment has to go to the river. This sediment is already there. So you can already see the banks are the major source of sediment in the Minnesota River Valley. So I had a student named David Thoma, some of you know, might have met him, and he took us in this route. Hey, this is the Blue Earth River, and you can say almost it's bare, although even in the winter time. And so he was the first one, he wanted us to use the LiDAR, so we used the LiDAR to calculate the extent of bank erosion. And then in 2010, Drew Kessler joined us, and I had commissioned a LiDAR in 2009, and state had a 2005 LiDAR and superimposed on this bank, and it shows where the bank was eroding. So this is where the sloughing occurred. This is where there was some deposition. And I'll show you this bank in some of the pictures. So based on that, in the Blue Earth County, we figured out we lost about 1.7 million cubic meter of soil over the 5-year period. These are the river banks that we monitor. In the Blue Earth is the main river. Waterman and Perch Creek were the tributaries of Blue Earth. And then Lasur River is the main river, and Maple, Big Cobb, and Little Cobb are the tributaries of that thing. So we also knew that bank materials have different parent material, mostly is glacial till, but there are also some banks which are lacustrine, alluvium. We took lots of sample in the field and measured the fine particles, silt and clay, for each of these parent material. We also measured the bulk density. So using the bulk density, we can convert that volume into the mass of soil that lost, and based on the silt and the clay, how much of the fine particles are going into the river. So using these calculations, we are looking at, they also have the measurement of how much sediment they measured at the mouth of Blue Earth and the Lasur River. So we are finding that 48 to 63% of all the measured sediment at the mouth of the Blue Earth River came from the river banks of the Perch Creek, Waterman, and Blue Earth. Similarly, what they measured at the mouth of the Lasur River, 61 to 79% of what they measured came from the river banks of Little Cobb, Big Cobb, Maple, and the Lasur River. So we knew that these are the major sources. These are, I think, on the low side because there are a lot of creeks that we did not look at it. So this was the extent of bank erosion. So we know that's a major source. Now I'm going to talk a little bit about the mechanism of bank failure in the Minnesota River Valley. Seepage is one of them. I just showed you in one of those pictures. Wetting and drying, freezing and thawing. This is what the agency folks have been kind of concentrating on. There's like a water is moving like a sandpaper, it takes some particles out and it undercuts the bank and they come down. We have not seen very much evidence. In fact, I would say I have not seen any evidence of undercutting. And then there is a channel migration because you have flooding and sometimes rivers are blocked and they move. And then ice gouging that I mentioned earlier. So in 2005, after seeing the banks, their water is hanging in some of those banks. I had a Nate Bartholomew working with me. And so we said, we are going to see if the seepage caused the bank sloughing or failure of the bank. So this is the Eagle Lake. There were trees over here, there are trees on this side, but this is a bare area. And we put a meter by meter area and we put piezometers and we put some tensiometers. And we were monitoring, we added some water by buckets because there was no concentrated source that we can easily get it. We'll have 10 buckets take over there and put the water, and nothing happened for a month or so, but it wetted up the soil quite a bit. And now this is a movie that you're seeing it. So when we were adding the bucket water, and then we brought the big tank of water and started adding the water. And this is, I put a paint over here because when we were putting the water by buckets, some of the soil was coming from here. And here's a tensiometer and a piezometer. And you'll see, this is the last 2 minutes of that 20-minute video, that we lost, there's a rotational failure in the bank, and we lost about 2 tons of soil, okay? And this is where the seepage is. The water hangs over there because of the glacial till, and there's a slope back there. The water is moving towards the bank, and it cannot get out until the bank gets saturated. And then when the water pressure builds up in the back, that's how the bank fails. What happened? So you'll see that about a 2 ton of soil we calculated. It just comes down because there's a water pressure in the back, and the whole bank was not saturated, okay? So this is pretty common. Here is a picture of the seepage. This is the Lusur River. This is in 2010. 2011, the trees came down. This is the driveway of this gentleman over here. He had to move the driveway. And he also put some riprap in front of that rock, in front of the that bank over there. Nate has taken this picture sometime late March or early April. This was on the Blue Earth River. And you can see the seepage caused this bank to come down. And as this bank was coming down, it also forced the lateral damage on this bank to come down. This is on the Blue Earth River, and Drew had put this picture together. This is Vernon Center. There's a sumac over here. There's sumac over here. This bank was attached to that thing. It's been slowly moving. I don't see any evidence of bank undercutting of these banks that's causing these banks to come down. There's also fine material due to weathering just kind of coming down on this bank. This is on the Lusur River. And over the winter, you can see that this bank is going into the river. And so there are a lot of houses over here, and there's a road, and they want to make sure there's a road over there. So over the winter time, the Department of Transportation in Blue Earth County put this riprap over there. And we were there on March 6th. There's a March 6th picture, and you can see the guard over here, road guard. And see what happened to the road guard? Even then, because of the seepage, this bank is still moving. So seepage is one of the bigger problem in this area because of the glacial till and water hanging over there. If you go over there and you'll see icicles, that's seepage. And you'll see during weathering, March 15, some of this material just kind of sloughing down. Okay, so there's a lot of weathering going on in this area. This is on the Maple River. This is the most dirtiest river in the Lusur River, those 4 rivers. See where the black material came from? It didn't come from here, it came from there. And there's a seepage spot over here because of glacial till. It was also probably thawing happening over there, and this whole bank came down. This is the bank that Drew had put that red and the blue colors in there using the LiDAR. This is August 29, 2013, and that's October 1st. Look at this bush over here. There's nothing in this part here. And during that thing, the bush came down and put the material right over here. Now, we can control the flow. That's their premise. Or let's control the flow, the sediment wouldn't go down. But you'll see that some years, if the water is a little bit higher, then this bank material will be taken out. It depends how much area it's covering, depending on different flows in the river system. If if this only covers this much surface area, then it's this material that will be taken out. If it's cover more surface area, then there will be more material taken out. This is a Big Cobb River, and we had contact with the kayak people in Mankato area. And so they called us and say, hey, there's a big bank slough over there on the Big Cobb, and it's crossed the river and blocked it. So we went over there in April. I am afraid of the water, and Drew, we didn't go over there in April, but when I went in August with Drew, river levels were low, and there was a lot of material in here. That'll be taken out subsequently. There's no tile drainage. There's no agricultural land over there. Okay. And when we were looking at this, we also saw there's a mud flow from an old scar that has happened. There's a water because of the hanging in there, and it's coming out. This is the tallest and the longest river bank on the Lusur River. And this was in October 30th. You can see the soil particle and aggregates coming over there from the top and accumulating over there. And now if you have a river flow in the next spring, it's going to be taken out. There's no undercutting of these river banks, as these guys have been saying. Now, this is a Lusur River. This is a floodplain area. This is somebody's house. His bank has been taken out. And you can also see, this was a 10 inches of rain in St. Clair upstream. I think there was another 2-3 inches on different date. And there was not enough space in spite of it was in September and there's plenty of space in the soil. So there was flooding in St. Clair and led to the flooding in the Lusur River. And this is the doctor's house over here, and the porch in the back is kind of gone. So I have not gone there since that time. I'm sure this has been taken out. And there were two other houses, they're a little at higher elevations. They were bought by FEMA because there's a water hanging and there's a seepage, and their backyard was just in the rivers. And river also moves. And when the rivers move, they also go and take some more material out. And most of the time, the river movement is because the trees are coming down and blocking the area, or the bank slumps and blocks the flow of the river. This is a 2009 air photo, and Drew had put together the position of the 1938 Blue Earth River. This is a one bank that we have monitored quite a bit. Look at how far it has gone back. This is that red and the blue bank that Drew had put together. Now I know in 2014 or 15, this is up on the hill. This is down near the valley. Leroy is a farmer in that area, and we work quite closely with him. But 2014, when we went over there to take pictures, the river has gone through this thing because of the blockage of trees and left a lot of trees in this area. So he spent about 3 weeks just cleaning up the area so you can plant his crop at that time. So those are the different mechanisms. Now, I plotted over here the sediment concentration versus discharge. And this is at Minnesota River at Mankato, again, divided into two portions, 68 to 91 and 92 to 2015. And there's a lot of scatter. Even at the same flow, we are getting a lot of variation. And part of the reason is this describes the randomness of the mechanism that are happening. Every bank does not slump at the same time. Every mechanism doesn't happen on the same bank, okay? And most of the time, the agency folks who are using other people's data, there's only a single line because they have 4 years of data or 8 years of data. And then they further summarize it by taking average values. So this randomness that you see over here is very important because it's telling us about the mechanisms. And the other thing that you'll notice is the low flow over here is close to 0.002 millimeter or 3 millimeter per day. So this is because blue is the early period because we had drier years. We didn't have a wet years. No, we have moved it close to about 0.1 because we have wet years. When you go on the other end, blue kind of stops over here. There are few points over here, but most blue stops here. But now we also have more flow at the higher end. And they are recommending, well, if you have 1 millimeter per day, above that water should be stored, or some peak values of those water should be stored. If you store it at one time and you have a next storm, you have no storage condition. That means if you're storing only for 2-3 months, then you got to have some mechanism to get the water out again back into the river. So once it goes back in the river, it's going to carry the sediment. If you have a 10 or 12 inches of rainfall, it doesn't matter. You have stored it, all the sediment that have been accumulating at the bottom because of sloughing is going to be carried out. Now, the individuals, they have not used the sediment concentration. It should be mostly, you should be using sediment concentration because it's an independent variable and discharge is an independent variable. They are using sediment loads, which is the concentration times the discharge. So they're correlating the discharge with the discharge. That doesn't make any sense to me. Now, even if you take a sediment load, you still have those mechanisms showing up. There's still some distribution that's telling us that if the water is stored, when you put it back in the river, it's going to take out those sediment that are sitting over there. Another study, they have used the month, they are further taking out the variation by using monthly sediment load. And they're calibrating it, and they use this calibration, monthly flow versus monthly sediment, and go back and take the prediction from the model and correct it. You know, their correlation was 0.99. Now, if you look over here, this is concentration, monthly mean concentration. That's a independent variable. This is an independent variable. Correlation is between 4.48 and 0.60. When you correlate the monthly load, that correlation is 0.9, 0.99, because you are multiplying concentration with the flow and you're relating with the flow. If there was no concentration, this will be R square of 1. So that's just a kind of going in circles and not using the right kind of scientific methods and publishing papers and coming up with some conclusion that are just not solving the problem. Now, they want to store the water on the land. There was a news in one of the local papers in Sanborn. It's close to Lamberton. And they are saying the ground is sinking, and the owner thought it was a earthquake. So we went over there, and this was a pasture. It's a hill slope. And on the pasture, you can see the lot of, crevices over there. And this rock, then we went back on the 23rd, and you can see the hill slope is still moving because the rock is splitting up a little more. This is Drew over here, that's Ashley Gretner, and that was the owner. So I asked him, what's on the top? He said, there's a flat field over there. And I said, what's in the backside? It's a pond over there. So this is the flat field. This is the hill slope, is a 1/4 mile long. And this is a little creek. He brought us over here in a pickup truck, and I saw some seeps over here. You couldn't see this pond from that angle. So that's the reason I was asking him. So if you have a lot of seeps, the hill slope is already weak, and you got 4 or 5 inches of rainfall on this bank over here, it's going to definitely fail. And so if you are storing water, and you are going to have a lot more erosion over there. This gentleman said this pond was put in 1950s. His dad was a conservationist for NRCS, and President Eisenhower came over there to inaugurate that, or he inaugurated that storage area over there. Those were the dry years. You needed water stored. We store the water in dry years, not in wet years. So the other comment they're saying is they're going to store it. They want $89 million or something, and that'll take care of the problem. This is Drew's work using the LiDAR. It's telling us the blue is the National Wetland Inventory, and red is the depressions. 25% of the top volume is in these depressions. They're far in between, okay? 50% of the top volume is in all these depressions. And 75% is in these depression, and 90%. So there are a lot of little depression, they don't have much volume. We also characterize this, it's a percent of observation. 98, 97% of all the depressions are less than 1 hectare. The depth is in all the less than 1 hectare depressions, depth is close to 15 centimeters average. So there is not much storage to hold the water. That means where are they going to put the water? Are they going to be putting some kind of dam? Are they going to be digging up the soil and putting the storage space? Third thing, crop productivity. This is a work that John Cully did. He was a student of Bill Larson. This work was done on Giles' plot over there. This is a tile drain plots. He put a piezometer over there and measured the water level after the rain. So this is the water table elevation. 0 is where the tile line is. And this happened later in the year. So there was some rain, and there's another 38 millimeter of rain over about a year and so, about a day or so. And you can see the water table goes up to close to about 0.9 meter. And it took close to about 10 days to come back. So if you store the water on a land, you're going to raise the water table. It's going to go to the next door's water table, and it's going to keep on putting the tile drain in the next door's plot over there, and nitrogen would be going out of that thing. Nobody's thinking about that kind of problem. This is a Nathaniel Balmer's student with us, and there's a couple of papers on this work that we have done. This is the Minnesota River at Fort Snelling. This is the Grand River from Missouri. This is a steep river, a steep landscape in the watershed. This is a flat landscape watershed. they have about the same amount of nitrogen was applied. There's a little bit more manure over here and a little bit more commercial fertilizer. If you have 800 millimeter of rainfall, you are going to have very small amount of nitrogen loss compared to the Minnesota River. It's partially because we have high organic matter soils too, but it's partially because a lot more water in this watershed is going through the soil. So 75 to 80% of the water in the rivers is infiltrating. Whereas in here, these are steep, this is a steep watershed, much of the water runs off. So even though precip is 800, there's only probably 100 or 50 went through the soil and took the nitrogen out. So now, if you're going to put more water on the land, you're pushing more water through the soil, you're going to have more nitrogen loss. So the implication of this part is there's not enough space to store the water on the uplands. And it'll change the water table, and there will be more drainage from the neighboring fields, and there will be less available storage for the next storm. There'll be decreased crop productivity because if the water level goes up a meter and continuously stays there, you can't grow a whole lot of crops. There's going to be increased nitrogen losses. And if you have water on the land, water is moving at the top of the impeding layer towards the river. And there are going to be a lot more seeps over there and a lot more bank erosion. So I think these guys got to start thinking about, we are getting all this money, how we are going to use it. So this was the bank erosion part in the Minnesota River Valley. Let's look at the soil erosion from agricultural land. This is how Des Moines lobe looks like. This is a picture from Iowa. There are a lot of depression. They're not very deep. They're interconnected. So water comes over here. It goes into this little depression, moves over here. It takes a long time before it gets to the ditch. That's why 75 to 80% of the water through this landscape infiltrates. Now, one of the problems with modelers is these are point models vertically. They do not look at how much water is running off. They think at this point, 20% ran, they think it went to the ditch. It's a three-dimensional problem, not a one-dimensional problem. This is in Iowa, northern part of Iowa. This is right in Mankato. And this gentleman, this was in Mankato magazine. He titled it Land of Million Lakes. And you see the little depressions over here, which are a little darker. Those are the depression where water sits. And we have these problems all the way up in the Des Moines lobe. So John Moncrief and Daniel Ginting, I got a freebie on this thing. John was interested in seeing to what extent the sediment and the water is going through the surface inlet, because most farmers have a surface inlet in these depressions. So there are two watersheds. He called it W20. 20 refers to 20-inch diameter pipe, and W15, 15 refers to 15-inch diameter pipe. And we were interested in seeing how much of the sediment, phosphorus, water kind of runs off through these surface inlets. So at Dorsey built a shed over here with all the instrumentation. This is how it looked like before the experiment started. Then early spring, it's all water is standing. And after main rainfall, water would stand. It wouldn't get out very much. And the reason is these depressions are linked with each other. There's a main drain pipe, and it's connected with that, and so on. And this depression would not drain until this depression has drained, because there's a back pressure. And nobody's thinking about those. These guys just store the water. Sediment are going to be less. They are not thinking of these consequences that there's not much water coming from this agriculture land. So I'm just going to show you some of the data. This is over a total of 3 years. 96 to 98, we had snow melt, rainfall, runoff, and total solid, which is the sediments. And we lost only about 138 kilogram of solids in over 3-year period per hectare. So it's a 44 hectare. So you can think about a ton or a two. Over 3-year period, that's not much of a sediment. You can put a rock inlet over there, or you can put a mine tailing, and this is 125. And these are not whole lot of sediment that going. into the river system. So that's the field erosion in the Minnesota River Valley. Now I'm going to just briefly show you some pictures because of the time. And I got into, the Red River Valley is flat like a pancake, okay? And this is because there was like Agassiz, there was lacustrine deposit. Glacier came many times. And so this has lacustrine as well as glacial material in the Red River Valley. And this is if I can make it work, I got a note from Warren Formo, and he says, you may be interested in, because we had worked on the Minnesota River. And it says, bean field collapses and fall 25 feet in rural Polk County. Near Climax, Minnesota, a small crack in the ground has grown, causing a quarter-mile long stretch of bean field to fall 25 feet. Few have ever seen anything like this. So let me see if I can make this work. This is a TV. Oh yeah, here. There's going to be a little commercial, so bear with it. So this is that picture looks like. This is from Brad's. I had talked to Arlene and Wayne because they were interested in talking to me because of our work in Minnesota River Valley. Nick Jelinski had gone there with Dave Hopkins from the North Dakota State University. Mark Dietrich from the MDA had gone. I can't travel, so I never got a chance to physically go over there and look at that. And Dave Hopkins, with his student, they took the LiDAR measurement, and it lost 27,000 cubic meter of the soil into the Red River. Well, one of the things that you want to see, and I think Wayne mentioned that, it's going backward. And the reason it's going backward is because the material underneath is getting out without carrying the top part, and that's why you are having these crevices. So it's like you're squeezing the toothpaste out of the toothpaste tube, and it's just kind of getting out, and top of the material is just kind of settling down that way. This is the material that came out underneath, that bank over there. You can see the trees are backward. And so all this material, 27,000 cubic meter, that's a lot of material. It went on the other side of the river. And my interest was try to see what the role this bank material plays in carrying the phosphorus to Lake Winnipeg. So I was talking to Carl and Nick Jelansky and Mark Dietrich, and we were trying to see if they'll be interested in that. And when I started looking in this research part, this is very common in that area. There's a road, it just kind of pancake just down underneath because the material under that went into the river. This is how the river, this is the Red Lake River, all the material just went underneath. This is a 1913 in Canada. They had an elevator and the material squeezed out and became unstable. And part of the reason is not only the wetness, but it also, as you're loading and unloading, you're changing the shear strength of that soil. And it just couldn't hold the material. In 1955, in West Fargo, there was an elevator only partially filled, newly built and partially filled. It just destroyed itself. So there was a gentleman at North Dakota State University, Don Schwartz. And in 2005, I had organized a symposium at the ASM meeting on bank erosion. I invited Don to come over there, and he said, this material floats. And he is saying is that as a result of 100,000, 200,000 a year, some of the shales from the western North Dakota, they were brought into the Red River Valley. And most of the material is a smectite clay, which absorbs the water very highly. So these are some geotechnical properties: plastic limit, liquid limit, and the bearing force. Now the plastic limit means you need 30% water in the soil to make a ribbon. Liquid limit means you need 85% of the water, so it becomes liquidy that you can put a line with a spatula and both sides of the soil would come together. So there is a shale rock formation, and below that is the Brianna formation and Hewitt formation. So it's the Brianna and the Hewitt formation which absorbs a lot of water, 113%. And that's what Don was mentioning about it kind of flows. And that's some material that goes out in the Red River. So he has a kind of a paper on the web, and he showed these diagram in there that if there's a crack developing, then the shear rock formation just goes into the river as a rotational failure. Whereas if you have a Hewitt and Brianna formation exposed over there, it's flowing underneath, and this material is just coming down. And that's exactly what happened on that road as well as in that bean field. So the extent of shear rock formation is this. In the Red River Valley, this is a Brianna formation, and this is a Hewitt, and this is that Polk County where the climax is and where the bean field went into the river. And again, going back to talking to Carl and Nick Jelansky and Mark Dietrich, my interest was because of our work here, the phosphorus in Lake Pepin was coming from, not from agriculture soil, but from the wastewater treatment plant. So my interest was, how is these material that are coming into the river, are they carrying the phosphorus either from agriculture land or from the wastewater treatment plant? Well, agriculture lands are very far away, so the only mechanism you can think about is flooding happens quite often in the Red River Valley. And so how is the phosphorus moving? Is it moving in one shot, in one flooding, and it moves part way and then comes back, second flooding? And also these wastewater treatment plants. You know, we didn't start treating for phosphorus until 1970s in the cities. And I am not sure when they start treating. So it'll be kind of interesting how much went from the sewage treatment plant as well as from agricultural land. So that was my interest, and I hope some student would pick it up. So in conclusion, it's a long seminar. Holding water on upland in the Minnesota River Valley will lead to more sediment production and increased nitrogen losses. We do not store water on uplands in wet climate. I don't know how else to say to these folks. If wet climate continues, we need to be thinking about how to create more storage. And one of the ways is either put more tile drainage in there or have surface runoff leaving some of the water, and so you have some capacity over there. And one of the ways would be rock inlet. I think if we have wet climate, we got to get the water out as soon as possible. So we have less water going through the soil and less nitrogen going through that into the river. And the Red River bank material may be a big carrier of agriculture and wastewater phosphorus to Lake Winnipeg. And I think that'll be an interesting question to resolve into it. So finally, there are many students worked on it. I have given out the sheet of publication that we have for the Red River. Yeah, and if somebody want, I think there might be still a few pages. Most of the details are in those papers, except for the sediment concentration discharge relationship. So with that, I'm going to stop over here, Tim, and if you guys have any questions, I'll be glad to answer them. Rock inlet is you have a pipe. You can put some rocks in there, so it'll slow it down, and you can put even mine tailings in there and it'll pick up the phosphorus as the water is going down.
Are those still going in today?
No, well, most farmers, I was surprised to hear some farmer telling me, oh, I got rock inlet in the field. They generally have replaced them with the tile
That's what I,
intensive, but there are people who have rock inlet. And one of those is one of the student in our department whose father has it.
so-
Yeah,
But in general, rock inlets are not being used.
no, rock inlets are not being used. It's a surface inlet, but this gentleman had a rock inlet on his property.
So the surface inlet.
Yeah.
That's still going into the tile.
It'll go to tile drain. Oh yeah, there's no other place. There's no other place to go. But because there is a back pressure from upstream depressions, it's still slowing it down. So water would go. There's no water, no way you can hold the water on the land. There's no other place. And the atmospheric demand is getting low because of the more frequent rainfalls.
Satish, I have a question. Can you hear me?
Yes, who's this?
Fabian Fernandez.
Oh, hi, Fabian.
Sorry I couldn't be there today, but really interesting presentation. One of the things that in trying to minimize nitrate leaching or nitrate loss to the rivers is to store water for the growing season. So basically use the tidal drains to drain the fields when we have excess water, store the water in like a wetland or something like that, and then reuse it in the summer. What are your thoughts in terms of that? Would that be considered kind of the problem that you were talking about, storing water, or would that not be a problem since you are, basically using that water during times of deficit in the summer?
I think that will be the same problem I've been talking about. I think nobody's, what's his name? At Lambert, and they did that experiment. And
Yes,
there was-
Jeff Strack
Jeff-
is doing some of that
Jeff
work right
Stark,
now.
yeah, he did that, and there was hardly any year. Look at it, how much water is coming over here? We don't have dry years when you'll need water many times. So this water is going to be sitting there, and you'll have to create a lot more storage space to hold that water and additional water. So I'm not sure, I think it's the same problem. That's what, the people in agencies have been using, or you can use it when it's dry. Even this year, if you heard Kenny Blumenfeld's presentation about a couple of months ago in Duluth, and he called it as a still warming, still rising temperature and getting more precip, but even in a drought year. So even we got 8-9 inches in the fall. Okay, so amount of water that falls on the land has not changed, even if there's a drought year in the during summertime this past year. And so that's a problem, because total water, how long are you going to store it? So I still consider the same thing. And Jeff had not measured, how much of the change in water table was in the neighboring field, or how much of the nitrogen was lost because of that practice. And I think unless you start doing some experiment and getting the data, at this stage, I think it's the same thing. And a part of the problem is nobody wants to do the field work. Everybody wants to run the computer model, which are point vertical models. And they don't tell you anything, even if these modelers think, I was a modeler too. And I believed in that for 20 years. And I think we gotta get away from the modeling and try to collect some data and based on that, make some judgment. Sorry, Fabian, if I'm negative.
That's fine, Satish. I appreciate your view on that. You know, as I always tell people, there are no easy solutions. If there were easy solutions, we would already figured it out. So
Carl?
If you did store the land on there, would you perhaps get more demarcation?
Yeah, there may be, but you gotta look at what other things you have impacted. You know, I mean, my idea in Nathaniel's paper when we wrote, you need wetland. A wetland is a good thing to have. I have no problem. Just don't do it on the uplands where the tile drainage is and agriculture. My idea was Mississippi River in 1865, they couldn't even bring the boats up here. There was not water. So they constricted the Mississippi River into a narrow channel, and it was 4 foot deep first and then 9 foot deep. And there's a lot of land which is a wetland. Well, why can't we put some water along that line? You need at least several months of water standing or moving through the wetland to have a major denitrification. You can't just have it today and tomorrow you say there's a denitrification. So you got to have a path that is running over there continuously and along the, Minnesota River too. There are some lowlands. But you go over here down by the Mississippi in the cities, they have put the dikes over there, and they have got building industrial area over there. They are not going to let you have wetlands over there. So my idea is put the wetland, but on the lower, right next to the river and not on the upland. My concern is more on the uplands. Yes, sir.
But if you do that, you're gonna have more water pressure right next to the bank.
Well, don't have it on the bank.
And then you'll have more erosion that you were talking about.
Right.
So I'm thinking the water acts only at the water level. It doesn't act above the water level.
What? You taking a soil physics?
What I'm saying is the river water doesn't work much above the river level.
What are you talking?
What you're talking about is bank sloughing, which is, yes, hydraulic pressure and others, that's fine. But something has to take that stuff away for the bank to advance. And that removal of the spoil
Yes,
is dependent on river flow.
yes, yeah,
And you were at one point saying, well, it's not the river that's causing that. Well, the bank can't advance any faster than the river can take the spoil away. And that is flow dependent. And that's why they're talking about storage, just like they are putting in large storage in the Red River Valley, has been going in for a long time.
yes,
And some of that is going in smaller scale in the Minnesota River Basin. If you look at County Ditch 57, for example, in Blue Earth County, ISG put that in. That's a drainage outfit. They engineered the storage into the drainage system so that they didn't have to have such a big conveyance downstream in the tile drainage system. They put the storage in the system. It comes in from the upper part. It stays there during high water and then goes out slowly afterwards.
you are going to, let's look at this diagram over here.
Yeah.
This water is here. It's going to take this material. This is slumping from the top. It's going to be moving some of the material. That's where the fluvial erosion, but it's not undercutting this bank to have top of the bank come down. That's what I'm trying to tell you.
Yeah, but the top of that bank can't move back until that spoils.
No, that's where your problem is. Top of the bank is already moving back.
Yes, but it can only go so far, and once it reaches a certain angle, it can't slope
Okay,
anymore.
all right. So
The material has to be removed, and that's going to go out at the rate of the high flows of the river.
sure, I don't have any problem that water is a carrier. Water is a carrier. The question is, if you are going to store all that water at the high end, first you don't have a space and you're going to get a lot more rainfall, then you'll have to put it back in the river. It's going to carry it again. And I don't know, I'm not sure what you're trying to say. I have not seen ditch 57. So that, there might be something, I know that they have spent in this, let me bring that. They spent in this river, they spent $500,000. Okay, they were putting J hook, they were putting willow seedlings, you know, Roscoe's classification, nothing happened. They had a 12 inches of rainfall, everything went off. That these people don't want to put rock over here. And if you put a rock over, you can stabilize that thing. So I think when you're saying store water, you're looking at only one thing, and that is we want to cut down the sediment. And you are going to have wholly series of other stuff that you guys have not thought it through. And I saw your comment on that. There was a website in Mankato. They were saying, okay, let's store the water, and it's a petition. And people have written comments over there. A gentleman's comment was, oh, we've done enough research. Let's go and do something. I mean, there has to be some science to do something. And we are not looking at the science. That, well, go back and look at it. I think we are past the,
Any more questions? Thank you, Satish.
yeah, thank you, guys.